Today, we're going to learn about something that is very magical to me, magnetic induction. To begin our exploration of magnetic induction, let's talk about a demonstration that I love to do in front of a class of physics students. So we'll say that there is some wily physics instructor who holds a long, narrow aluminum tube and two cylindrical objects. One is a magnet and the other is not magnetic. He then drops the non-magnet through the tube and it falls through as expected. He then drops the magnet through the tube, but it takes much longer to fall than the non-magnet. Why? Well, one thing you should know about this is aluminum is not magnetic. So if I were to take a magnet and hold it up to an aluminum tube or an aluminum can, it wouldn't stick. Yet here, if I take a magnet and drop it through this aluminum tube, and even if it doesn't touch the sides, that magnet will take longer to fall than a non-magnetic object falling through the aluminum tube, even though aluminum is not magnetic. To me, that is magic, and it makes me wonder why that is. The answer to this question lies in magnetic flux. A changing magnetic flux will induce charges to move in a conductor in such a way that the moving charges will create their own magnetic fields to oppose the change of magnetic flux. You're probably wondering, what does this have to do with what I've just said, with the magnet falling through this non-magnetic tube at a slower rate than a non-magnet falling through? Well, to understand this, we have to talk about what magnetic flux is. Magnetic flux is the amount of magnetic field passing through a surface of area A, and is proportional to the number of field lines crossing that surface. What we have here is a surface of area A. The vector normal to that surface gives us the orientation of the surface, and that is what we are going to compare the magnetic field to. Notice in this picture, that surface, we'll say this surface is parallel, or the surface area vector is parallel to the magnetic field. They're pointing in the same direction. So the angle between the magnetic field and this normal vector is 0 degrees. Notice the number of field lines passing through the surface. I count 5 magnetic field lines. When we change the orientation of the surface relative to the magnetic field, fewer field lines cross the area. So here I count 3 field lines, whereas when the angle between the magnetic field and the surface area vector was 0 degrees, we had 5 field lines. Now the angle is some non-zero value. We have fewer field lines crossing the area. Notice when the surface area vector is perpendicular to the magnetic field, no magnetic field lines cross the surface. None pass from one side of the surface to the other side. Here, we would say we have 0 magnetic flux because there are no field lines crossing the surface. Well, let's take a look at this from a different perspective. So here we've just changed our perspective. We are looking at the loop, at the area, from the direction of the magnetic field. So the X's that you see in the screen represents that the magnetic field is moving away from us. So if you look at the top image, that would just mean that we are looking at this area from the left-hand side. Notice the number of field lines crossing that area when the angle between the magnetic field and the surface area vector is 0. If we increase the angle to a non-zero value, notice there's significantly less magnetic field lines crossing the area. So the magnetic flux has decreased because magnetic flux is directly proportional to the number of field lines crossing a surface area. And when the magnetic field is perpendicular to the surface area vector, notice zero field lines pass through, so we have zero flux. So if we look at this sequence, when the angle is 0 degrees between the magnetic field and the surface area vector, we have maximum flux, the maximum number of field lines crossing the surface. When the angle is some value between 0 and 90 degrees, we have an intermediate amount of magnetic flux. It's not the maximum amount of flux because not all the magnetic field lines are passing through, but it's not zero flux either because there's at least some magnetic field lines passing through. And then again, when the magnetic field is perpendicular to the surface area, we have zero magnetic flux because of zero field lines. Well, this behavior can be summarized in a relationship. We could say that magnetic flux is a measure of the amount of magnetic field B crossing a surface S of area A, and it's given as the surface integral of the magnetic field over the surface. So notice what we have here. We have an integral over a surface of the dot product between the magnetic field and the surface differential. This dot product right here, remember, signifies a relationship between the magnetic field and the surface differential. We could rewrite this dot product in terms of the product of the magnitude of the magnetic field, the cosine of the angle between the magnetic field and the surface area vector, and the magnitude of the surface area differential. So here's the angle dependency right here in the magnetic flux. Cosine makes sense because we have maximum magnetic flux when the angle is 0 degrees and cosine of 0 degrees is 1. We have zero magnetic flux when the angle is 90 degrees and the cosine of 90 degrees is 0. Now, this formula is great when we have a non-uniform magnetic field or when the magnetic field varies across the area. For most of the problems in this class, the magnetic field will be uniform over the area. And when that's the case, the surface integral simplifies to be just this, the dot product between the magnetic field and the area vector of the surface. Now, the unit of magnetic flux is called the Weber. Now, 1 Weber is 1 Tesla meter squared.